Welcome, everyone. For today's prep, we're going to continue on with this precise definition of the derivative, but now we're going to see what does this mean when we're looking at the graph of the function. So we're going to see if we're given the graph, how can we use that to determine whether a function is differentiable at a point? And then we're also going to introduce this idea of continuity, but we'll be doing that in class. All right, so let's recall, we've got our limit definition of derivative here. So this is our precise definition. So we say that a function is differentiable at a point x if this limit exists. So we can calculate the derivative here using this limit definition. Limit as h goes to 0, f of x plus h minus f of x all over h. And if we remember, the derivative here is giving us the slope of our tangent line. And the f of x plus h minus f of x all over h, that's the slope of the secant line connecting points P and Q. And then this limit in front is where we essentially take that second point Q, we slide it along the curve and get it closer and closer to point P. So just kind of keep this in mind. The derivative, what we're doing with the derivative is, again, this is giving us the slope of our tangent line. And by calculating the limit of the slope of our secant line, we're kind of moving that second point Q closer and closer to point P. So we want to keep in mind that's what the derivative is calculating for us. It's giving us the slope of the tangent line at x. Okay, so if this limit exists, our function's differentiable. But as we've seen, things can go wrong with limits. So sometimes this limit does not exist. And, what can happen? Why does this, why could this limit not exist? Well, as we've seen, sometimes the right and the left sides don't match up. So that's usually where things can go wrong. All right. So graphically, again, if we're keeping in mind the derivative is giving us the slope of the tangent line, really what that's saying is in order for it to be differentiable, we need to be able to draw the tangent line. So that's kind of the implication here. If we're looking at the graph of our function and we find a point that we're interested in, we need to be able to draw the tangent line. So where are places where we can't draw the tangent line? Well, there's kind of three groupings here. So we say a function is differentiable provided its graph does not have any of the following. So there's no jumps, breaks, or holes. There's no sudden changes in slope. And there's no vertical tangent lines. So if our graph has one or more of these, then we would say that point is a non-differentiable point. So let's look at a few examples. So we got a whole bunch of graphs here, and we're just going to investigate, and we're going to briefly explain why each of these functions is non-differentiable at x equals 2. All right, so, and again, keep in mind, we want to be able to draw the tangent line at the point. So let's start with the first graph here. So we're looking at x equals 2. We find the point on the curve, and we want to be able to draw the tangent line. So if this is the point that we're going to work at, well, if we draw the tangent line kind of using a secant line, a point a little bit to the left, it's going to give us kind of a slope or a line that's pointing in this direction. But if we use our secant line with a second point that's a little bit to the right, we're going to have a tangent line that wants to look like it's going in a different direction. So the tangent line from one side of the curve is going to look like this. The tangent line from the other side of the curve is going to look different. So there's no good way to draw one single tangent line at this point. So if we see something like this, where our graph has this kind of sharp look to it, has a sharp change in the slope, it's non-differentiable. So a lot of times we call this a corner or a cusp. But really what we're seeing is a sudden change in slope of our graph. So if we're looking, in this case, the left side of our graph wants to have like a positive slope, and the right side of our graph wants to have a negative slope. And it doesn't smoothly transition. It just has this abrupt change. We go from positive to negative, and it comes to a point there. All right, so that's one example. Now let's look at the next example for this one. So in this example, why does it have a non-differentiable point at x equals 2? Well, if we were to draw our tangent line there, our graph for a moment wants to kind of looks vertical. So this one has a vertical tangent. So with a vertical tangent, if we kind of think what the slope is, well, for this graph, the slope almost wants to be like positive infinity. So if our graph has a vertical tangent line, we kind of go back to our limit definition. What happens is this limit is going to infinity, or maybe minus infinity. But for our graph, the one we're looking at, it's going to positive infinity. So this vertical tangent line that we have here, it's almost like our tangent line wants to have an infinite slope. So that makes it non-differentiable. Infinity is not a number, so that limit doesn't exist. All right, what about the other three graphs? Well, all of these are kind of similar in a way, because for these graphs, if we look, the first two we did, the points that we were looking at actually were on the curve. There was a filled in point on the curve. The issue was, in the first case, the tangent line kind of wanted to be doing two different things. And then in the second case here, the tangent line wanted to be vertical. So those caused issues. But in these two cases, there actually was a point on the graph. Now, in the second row here, some of these, there's not even a point on the graph. So if we look at, say, this middle graph here, we have the left side of our curve, we have the right side of our curve, but if we look at x equals 2, there's actually no filled in point. So how can we draw a tangent line there? There's no filled in point. And even still, if we're looking at this graph, there's kind of an infinite jump. So we're going from the left side, and then our graph is going up and up and up. And then all of a sudden, we're on the other side, and our graph is going down and down and down. So we would say this has a jump. And if we wanted to, we could say it's an infinite jump. So the limit on each side of our graph is going up to infinity. So how could we draw a tangent line at x equals 2, even if there was a filled in point? How could we draw a tangent line there? Because on either side, the graph is going up and up and up. All right, what about our first graph here? So this is another jump. So if we look, there's a break in our graph here. So we would call this just a plain jump. So if we're reading left to right here, we're going, and then we jump and we keep on going. So there's no good way to draw a tangent line. Even though there is this filled in point here, there's no good way to draw a tangent line, because if we're using a secant line that's kind of coming from the right side, our tangent line would want to look, something like this. Fine. But if we're using a point that's coming from the other side to get our secant, and we imagine moving that second point closer and closer, well then as we get closer, our tangent line from that side wants to be vertical. So there's a difference between how our tangent line would look using the right side of our graph versus using the left side of our graph. So again, when the left and right sides aren't matching up, the limit doesn't exist. Now for this last one, well, again, there's a point missing. There's a hole on our graph. So there's no way we can draw a tangent line there. The point actually has to be on our graph. So if that point was filled in, yeah, it would be differentiable. But because that point is missing, well, we can't draw a line there. So we would call this like a hole. And that kind of covers all three cases here of what you might expect or what you can see if a function's non-differentiable. So if our graph has a jump or a break or a hole, then it's a non-differentiable point. If our graph has a sudden change in slope, so we have a corner or a cusp, then we have a non-differentiable point. And if we have a vertical tangent, well, that's also a non-differentiable point. So these are kind of the three different cases where our function could be non-differentiable. All right, so in class, we're going to see how this relates to a second idea called continuity. And well, we'll look at the limit definition of continuity. So we'll see you then. Bye-bye.